All right, everybody. This is the video for the second exam practice problem set. When you're studying for the test, you should probably go through this closed book and see where you're at before you look at the answers, and then try to figure out what things you're missing. So in this video, I go through all the problems. The answer to the problem set is always given to you guys at the end. There's a answer key. So you can skip through the video just to find the problems that you're needing answers to. So I'm going to go through these problems. So the first question says the reaction A goes to B is first order with respect to A. A solution is prepared with the concentration of A at 1.22 molar. The following data are obtained as the reaction proceeds. Okay, and it gives you a table of the concentration of A over time. And then we're asked for the rate constant. So important information in the question is when they tell you it is first order, a first order reaction, it has an important relationship with the half-life. So half-life is the time it takes for half of the starting material to be used up. So T1/2 for a first order reaction, 0.693 divided by K. Okay, so this is an important relationship between the T1, the half-life, and the K. So this is given on your formula sheet, but you need to know when to use it. You use it when there's a first order reaction. All right, so looking at the data, we start at 1.22 and then we go down to 0.61. So that's half, okay? So we have our half-lives. So every 6 seconds, we lose another half of the concentration. So our T1/2 is 6 seconds. So we're gonna solve T1/2, 0.693, K. We're gonna solve for K, 0.693 over 6. Our K is equal to 0.1155, 1 over seconds. And let's see, that's answer letter E. All right, our second question. At elevated temperatures, dinitrogen pentoxide decomposes to nitrogen dioxide and oxygen. When the rate of formation of O2 is 2.2 times 10 to the negative fourth, the rate of decomposition of N2O5 is blank. So this is one of the first things that's covered in the chapter, where we're writing out the rate of change based on the reaction stoichiometry. So for this reaction, we can write negative 1 over 2, and that's our coefficient on the reactant, delta concentration of N2O5, that's our change in concentration over change in time. And that's equal to 1 over 4, delta concentration of NO2, change in time, which is also equal to 1 over 1, change in concentration of O2, change in time. So this relationship you can write for any reaction. This is an instantaneous rate. And we're going to use, we have O2, so we have this part, and we want this part. And we want to know what the rate of decomposition of N2O5 is. So we can just use part of the equality. So we're just going to use our portion of the equality that relates N2O5 to O2. And I'm going to drop the 1 over 1 because we don't need it. So when we want to find this, we're going to multiply both sides by -1 or -2. So So I'm going to plug this value in that we're given, 2.2 times 10 to the negative fourth molar per second, -2. So the rate of decomposition T is equal to 4.4 times 10 to the negative fourth meters, or molar per second. All right. So it's actually asking for the magnitude of this number, so that's why you don't see any negative numbers. But this basically signals to us the rate of decomposition, that it's decomposition rather than formation. So the answer is D. All right, let's see. So we have data in the table for this reaction over different experiments where we're changing the concentration of starting material and measuring the rate. And it asks us, what is the order of the reaction with respect to ClO2? So what we want to do is find two of the experiments where the other reactant, which is OH minus, is kept constant because we don't want two different variables changing the rate of reaction, and where ClO2 is changing. So we're going to look at the first two experiments. That's where OH minus is staying the same and the concentration of ClO2 is changing. So in our reaction, we go from 0.06 molar to 0.02 molar. So we triple the concentration. Our rate goes from 0.0248 to 0.00276, and that is about 9. Okay, so now we're going to solve for the exponent. So basically, when we read our rate law, rate is equal to, or K times ClO2 X and then OH minus Y. We're looking for this exponent. That's going to give us the order of the reaction with respect to ClO2. So basically 3 to the X equals 9. So what power can we raise 3 to get 9? That's 2. So our answer is C, 2. All right, so under constant conditions, the half-life of a first order reaction, blank. So recall that our T1 half is equal to 0.693 over K. So 0.693 is constant and K is our rate constant. So T1 half is constant. Nope. Does not depend on the initial reactant concentration. Are there any concentrations in this equation? No. So it does not. Is the time necessary for the reactant concentration to drop by half of its original value? This is the definition of half-life, so it's definitely that. Can be calculated from the reaction rate constant. So if we know K, we can find T1 half. If we know T1 half, we can find K. So all of the above are correct. All right. A catalyst can increase the rate of reaction. So, so a catalyst basically is related to the activation energy. Say this is our reactants, products. Our activation energy is this energy required to go on for the reaction to move forward and form products. So a catalyst can change how a reaction occurs and lower the activation energy. So letter A, by providing an alternative pathway to the lower activation energy, yes, this is how the catalyst works. If this energy is smaller, it's more likely that there's that amount of energy, so the reaction is happening faster. So that's how the catalyst works. So we know that it's A, changing the value of the frequency factor. The frequency factor, A, doesn't have anything to do with the catalyst. The only thing the catalyst does is lower this activation energy. Lowering the activation energy of the reverse reaction. We don't want the reaction to go backwards. That's not going to increase the rate of the forward reaction. Increasing the overall activation energy, if we have higher activation energy, it's more of a barrier to form products. So that's definitely not true. So all the answers are not true. So our answer is A. All right. Question number 6 gives us a possible mechanism for the overall reaction. Okay, and it wants us to write the rate law based on this mechanism. So when you're looking at reaction mechanisms, it's a proposed way that this reaction proceeds. So, sorry, the proposed way that this reaction proceeds. So what you want to look at in the mechanism is the slow step. That's going to be, you know, the rate limiting step. So we're going to write the rate law based on the slow step as written. So rate is equal to the concentration of NOBr2 times the concentration of NO. Got my K. And then, so then you're going to evaluate this. You cannot have anything in the rate law that doesn't appear in the overall reaction. So if given this overall reaction, you can't have anything in the rate law that doesn't appear in the overall reaction, but we do have this intermediate. So we need a way to get rid of this intermediate. And really the only way to get rid of this is in the case where we have this reversible fast starting step. And that's possible because this reaction is equilibrium. So the rate of the forward reaction is equal to the rate of the reverse reaction. So our forward reaction rate is equal to K1 NO Br2. And then our reverse reaction rate is equal to K -1 NO Br2. So these rates, the value of these rates are equal. So we can set this part of it equal, so we can isolate NOBr2 and plug that into our intermediate. So K1 NOBr2 is equal to K -1 NOBr2. We want to isolate our intermediate so that we have something to plug in to our slow step rate law. So NOBr2 is equal to K1 over K -1 NOBr2. So we're going to plug that into our slow step rate law. So instead of NOBr2, we're going to plug in this value. Okay, and then our last step is to combine the terms. Okay, so rate is equal to K2 times K1 divided by K -1 NO2 squared Br, the concentration of Br2. So we're going to look for that. And then let's answer letter B. Okay, so number 7, it says for the first order reaction, a plot of blank versus blank is linear. Some people like to memorize this. I like to look at the integrated rate law, because the integrated rate law is a linear representation of that type of reaction. So the first order integrated rate law, which is given on the exam, is ln AT is equal to negative AT plus ln A0. So this is the integrated rate law for first order reaction. So this is your y equals mx plus b, your equation of a line. So this is going to tell us what we're comparing to look at something that's first order. We want to confirm that's first order by finding the linear representation. So if we plot ln of the concentration of our reactant by T, then that will give us a line. So the answer there is C. All right, so the half-life of a first order reaction is 13 minutes. If the initial concentration is 0.085 molar, it takes blank minutes for it to decrease to 0.055 molar. So it's giving you the half-life, and it's giving you that this reaction is first order. Because this concentration is not exactly half, we need to use the T1/2 to find K, and then use our first order integrated rate law to find T. So T1/2 is equal to 0.693 over K. K is equal to 0.693 divided by 13 minutes. K is equal to 5.33 times 10 to the negative 2, 1 over minutes. All right, so now we have our K, we know our concentrations, we're going to plug this in. So we have ln, and this is our final concentration, ln of 0.055 molar equals negative 5.33 times 10 to the negative second, 1 over minute, times T, we're looking for T, plus ln of 0.085. So we plug these into our calculator. Negative 2.90 equals negative 5.33 times 10 to the negative 2, 1 over minutes, times T, plus negative 2.47. I'm going to add 2.47 to both sides. And then we're going to divide both sides by 5.33 times 10 to the negative 2. And we're going to get our T is equal to 8.15939. So our answer is letter B. All right, looking at the last question, in general, as temperature goes up, reaction rate, hopefully your gut reaction at this time is that it is going to go up. But this question is more, does the rate of the reaction depend on if it's exothermic or endothermic? And this is something that you might get confused with Le Chatelier's principle, because that has to do with, you have to decide if a reaction is exo or endothermic. But when we're talking about reaction rate, it doesn't matter if the reaction is exo or endothermic. So it's definitely going to go up if the reaction is exothermic. It's not going to stay the same, because when we heat it up, we put more energy in there, so we're going to have a faster reaction rate. It's going to go up regardless. So that's our answer. And it will not stay the same. So your answer there is C. All right. Number 10. Consider the following reaction. The average rate of appearance of C is given by delta change in concentration of C divided by change in time, comparing the rate of appearance of C and the rate of disappearance of A, we get, so it wants us to rearrange our instantaneous rates. So we're going to write that as the reaction is written. Change in concentration of A, 1 over 1 over change in time is equal to 1 over 2 negative. Change in concentration of C, because it's negative because this is disappearing and this is being formed. So if we solve this for just this value, we're going to multiply both sides by 2. So we're going to get -2 . Okay, so just this is tricky. They included the negative sign in here. So the value here is only 2, it's positive 2. Luckily, they haven't given you -2 as an answer as well. That's just tricky. All right, the decomposition of antibiotic in a person with a normal temperature of 37 degrees C gives you the rate constant. For a person with a fever at 38.3 degrees C, gives you the rate constant. What is the activation energy for this decomposition reaction? So towards the end of that chapter, you guys talked about activation energy and how it's related to the temperature and the rate constant. So on your formula sheet, you're given ln K2 over K1 is equal to EA times R, or divided by R, 1 over T1 minus 1 over T2. So what we're solving for is EA, our activation energy. So, you know, it doesn't matter which one you label 2 or 1, you just have to keep them consistent. So ln 3.1 times 10 to the negative 5, 3.9 times 10 to the negative 5 equals EA over 8.314 joules per mole K. I usually remember which gas law constant we're using because we're talking about activation energy, so we need an energy unit. I'm going to pick the one that's in joules. And we're going to convert our temperatures to Kelvin. And then we're just going to solve for EA. So when you do this, negative 0.22957 equals EA divided by 8.314. Drop my units. And then this value is negative 1.3471 times 10 to the negative 5th. Divide by 8.314. EA times negative 1.62 times 10 to the negative 6. Don't lose your signs. And then finally, we're going to get EA is equal to 1.42 times 10 to the 5th joules per mole. So our answer there is C. Answer there is A, which is negative 5. Sorry. I think that's the last of our rate kinetics questions. So, bear with me. Sorry, guys. All right. This is what you want. Okay. Sorry about that. So the KEQ for the equilibrium below is 7.52 times 10 to the negative second at this temperature. And it wants the KEQ at the same temperature for the following reaction. If we know the KEQ for a reaction, and we do something like reverse the reaction or multiply the whole entire reaction by a number, by an integer, we can find the new KEQ. So if we want to find the reverse, let's say this is K1, K2, we want to find K2. K2 is equal to 1 over K1. You guys solve that, 13.3. Our answer is B. If we were multiplying, we would do something different to get our K's. So the equilibrium constant for the gas phase reaction is 4.34 times 10 to the negative third at 300 at equilibrium. And then it talks about the different ratios of products and reactants. So our KEQ value, the magnitude of that number, can tell us a little bit about if there's more products or reactants or kind of not, kind of equal. So if KEQ in this case is much smaller than 0, we consider that KEQ is equal to the concentration of products divided by the concentration of reactants. So if KEQ is very small, that means that our products concentration are probably small and our reactant concentration is probably large, which will make our KEQ very small. So we're looking for the answer where reactants is the bigger number. So roughly the equal amounts, note that's when KEQ is around 0, closer to 0. It's definitely not only reactants because we're talking about a reversible reaction, we're talking about equilibrium reaction, so all products and reactants appear in some quantity. So this one, answer C, reactants predominate. They're definitely wrong. All right. Number 14 is a question about Q. So Q is written the same as our KEQ, but it's giving us, we don't know if we're at equilibrium yet. So we're trying to find out if we're at equilibrium or which direction we need to shift to reach equilibrium. So it's written the same, products over concentration of products over concentration of reactants. So let's look at our answers. Which of the following is true? Q does not depend on the concentrations or partial pressures of reacting components. Since it's written the same as KEQ, and it definitely depends on concentrations, this is not true. Q is the same as KEQ when a reaction is at equilibrium. Yep, that's definitely true. Q does not change with temperature. So anytime you're given a KEQ, usually given a temperature, because the KEQ is different at different temperatures. So if KEQ changes with temperature, so does Q. K does not depend on the concentrations. We already decided that it definitely depends on the concentrations. KEQ does not change with temperature, but Q is temperature dependent. That's not true. So our answer is B. All right, number 15. For the endothermic reaction, and then it asks about how the Stratilius principle applies to this. Before I go into this, I like to represent energy in the reaction so that I remember which way it's going to shift. So in an endothermic reaction, energy is required. You need energy in endo. So I write that on the reactant side of our equation. The other thing I like to look at is moles of gas, 0 moles of gas. And we have 1 mole. Yeah. All right. So Le Chatelier's principle predicts that blank will result in an increase in the number of moles of CO2. We want to shift the reaction towards products. Okay, so to do that, if we increase the pressure, it's going to shift away from the higher number of moles of gas, because that pressure is pushing on the gas. So if there's less moles of gas, then it's better. So if you increase the pressure, it's going to shift away from the moles of gas. So that's not what we want. Remove some of the CaCO3. If we remove the starting material, the equilibrium reaction will shift back towards reactants to form more CaCO2. That's not the answer. Decrease the temperature. So if we decrease the temperature, again, we're going to shift back towards the energy as I've written it into the reaction. So that's definitely not true, or that is true. That's wrong. Sorry. So if we decrease the temperature, sorry guys, totally just got confused with the next question. As I said, decreasing the temperature, this is going to lower our energy. It's going to shift back towards reactants because energy is a reactant, not the answer. And then increase the temperature, that's the opposite. So we want to form products. So that is the answer. All right, number 16. Again, this is a Le Chatelier's principle question, and I'm also going to do the same thing. I'm going to add energy. This is giving us the delta H rather than saying it's endo or exothermic. If delta H is negative, that's an exothermic reaction. So we have plus energy on the product side. Heat is evolved when this reaction occurs in the forward direction. And then we're going to look at the number of moles of gas. We have 2 moles of gas. And then over here we have 3 moles of gas. All right. So we want to maximize the concentration of CO at equilibrium. So in order to do this, we need to shift our reaction towards CO2. So in order to do that, you're going to want low pressure because this side has the lower or the higher number of moles of gas. So we want lower pressure so it's not tending to go back to the starting material. And we also want low heat, because if it's hotter, it's going to shift away from the energy as the product and form reactants rather than products. So we want low temperature and low pressure. High temperatures are no. Our answer is C, low temperature, low pressure. All right, number 17. Fun. Gives us the equilibrium constant Kp for this reaction. Says that a closed vessel is charged with 36.1 atmospheres of NO, and then it asks for, once this reaction comes to equilibrium, what is the partial pressure of O2? So I like to write out our Kp expression. Kp is equal to N2, concentration of N2, concentration of O2, divided by the concentration of NO squared. So we know our Kp, we know what we started with for NO, but we want to find the equilibrium concentration of O2. So in order to do that, we're going to use an ice box. 2NO, O2, ice. All right. So it tells us that the reaction is started with 36.1 atmospheres of NO, but it doesn't tell us anything about N2 or O2. So So we're going to assume those are 0. Going to form some amount of N2 and some amount of O2, which are the concentrations will be the same. And it's going to lose 2x of the NO, the starting material. So at equilibrium, we have some amount of N2, we have some amount of O2, and we have 36.1 minus 2x. I will tell you that this problem, you cannot neglect 2x. I would not put this question on the exam. It's just a practice problem. So I probably should have changed the practice problem, but bear with me on this one. In this case, you cannot neglect x. I would not give you an exam question where you would end up with a quadratic equation. In this case, we don't end up with a quadratic equation, which is why it's not so challenging. We're going to keep solving it. So our Kp is 2.40 times 10 to the 3, and that's equal to x squared divided by 36.1 minus 2x squared. So both of our terms are squared, so we can take the square root of both sides to solve this. 48.99 is equal to x divided by 36.1 minus 2x. We're going to multiply both sides by this value, 48.99 times 36.1 minus 2x equals x. We're going to distribute the 48. Going back to high school, 1769 minus 97.98. X is equal to x. I'm going to add 97.98 to both sides. Good algebra practice. And then we're going to finally solve for x. X is equal to 17.9 atmospheres. That is equal to our concentration of O2, also equal to our concentration of N2. So let's find that answer. There it is. Letter E. All right. Question 18. A reaction vessel is charged with hydrogen iodide, which is partially decomposes to hydrogen and iodine. When the system comes to equilibrium, and it gives you the equilibrium concentrations of the products and reactants, and asks you to find Kp. So our Kp expression is concentration of H2 at equilibrium, concentration of I2 at equilibrium divided by concentration of HI at equilibrium squared. We can plug these values in and solve for Kp. 0.0960 squared divided by 0.708 squared. Kp is equal to 1.84 times 10 to the negative 2. So the answer, hey, I didn't show you guys any of the problem while I was doing that. I'm sorry. So our answer is letter B. All right. Sorry about that. So number 19. Given the following reaction at equilibrium, if Kp is 0.99, what is Kc? So this uses an equation that's given to you guys on the formula sheet. Kp is equal to Kc RT changed in number of moles. So delta N changed in moles of gas. If there is no change in moles of gas, then Kp is equal to Kc. So let's look at our reaction and see what's going on. We have 1 mole of gas going to 2 moles of gas. So we do have a change, our delta N is equal to 1. So we do need to solve for KP. So we're going to solve for KC. Sorry. So KC, rearrange this equation for my unknown, is equal to KP over RT raised to the delta N. So this is equal to 0.990 divided by, in this case, we're going to use the other value of the gas constant, 0.0821 liters atmospheres. And the way I remember this one is mole per liter is molarity, and we're talking about concentration. We usually use units of molarity. And then I've converted the temperature to Kelvin. We need a Kelvin and our gas constant, 523. And this is all raised to the first power. So when you guys plug that into your calculator, you should get KC is equal to 2.31 times 10 to the negative 2. And that's answer A. All right, let's see what else we got. I'm going to actually move it down this time. All right. The KP for the reaction below is 1.49 times 10 to the 8th. An equilibrium mixture of 3 gases gives you CO, Cl2, and it asks for what the concentration of Cl2 is. So we're going to write our KP expression. KP is equal to the concentration of Cl2 divided by the concentration of CO times the concentration of Cl2 at equilibrium. When we rearrange this, concentration of Cl2 is equal to Kp times our concentration of CO, concentration of Cl2. So our Kp is 1.49 times 10 to the negative 8th times 2.22 times 10 to the negative 4th squared. Solving that, plugging that into our calculator, we get 7.4. So that's letter A. All right, number 21. If the rates of the forward and reverse reaction are equal, the reversible reaction is said to be, and this is just the definition of equilibrium, that the rate of the forward reaction and the reverse reaction are equal. So they're said to be at equilibrium. So good luck preparing for the exam, you guys. Please email me any questions you have. Again, try to take this as a practice test. When you think you're ready for the exam, try to take this. And I know that we're already at the end of the video, so you've already done things. But in the future, you can also consider to do this. I think it really gives you an idea of what concepts and things you need to work on, because we don't always know that until we start actually solving the problems out, what we're not understanding. So thanks, and